Um, so Jaeyeon will tell us about how we should stop thinking so digitally and smooth everything out. My apologies if that's a terrible intro, but I'm really looking forward to this talk. So please take it away.
Hi, I'm Jaeyeon from MIT, and I'm currently fourth year PhD student and advised by Saman and Joel Emmer. I'll talk about our recent work in progress, the continuous tensor abstraction, which is a collaboration with Willow, Joel, and Saman. In the real world, many applications works on the continuous domain, like functions in numerical computing, managing spatial databases, 3D point clouds, and computer graphics. However, as you might know, manipulating such data has non-trivial challenges. For example, in spatial databases, the challenge lies in storing these geometries. It often requires very complex data structures such as quadtrees. For example, in a famous handwritten C++ library called GEOS, it takes approximately 500 lines of code to execute a 2D range search query over geometries. And here's another example with 3D deep learning on point clouds. In a well-known method for 3D point cloud called kpconv, the main idea is really simple. However, turning that idea into an actually efficient program takes a large amount of code, like around 2,000 lines of PyTorch. And many computations on discrete integer grid can easily fit in this way of thinking, like matrix vector multiply, but this is not sufficient for continuous domains. So in this talk, I want to share about the continuous tensor idea, which gives us a fun way to program with loops and tensors. So compared to integer index access like a bracket 2 or discrete loop iteration, our new idea suggests accessing tensor using real number index like a bracket 3.1415 and using continuous for loop that can keep going through an infinitely large range of real numbers. So to show you what this abstraction would look like, I've set up a very simple comparison using the dot product as an example. In regular programming languages, here's how you would write the code to perform the dot product between two vectors. And the most natural extension of dot product into the real domain is using now real number coordinates as shown in the blue and the red dots for the vector x and vector y. Now what we are suggesting is users will write the exactly same code as they would do for the regular dot product, but with a change in the semantics of the for loops. So the for loop now, you can imagine this iterates continuously. So imagine you iterate this domain very smoothly and perform multiply and accumulate for every single point. You would realize the effective multiplications between non-zeros only occur at 3.0 and 5.1. So this code will result in variable s being 44. And another example I like to share is how a vector, continuous vector, can have a data spread out continuously, as shown in the bottom left figure. Now we refer such coordinates as interval coordinates, and we call particular point coordinates in the middle example as pinpoint coordinates. So one thing very important to note here is that we rely on the assumption that all the tensors, continuous tensors, should be piecewise constant at this moment. So that being said, the tensor should only have finite number of non-zeros pieces, where each piece is a n-dimensional axis-aligned bounding boxes with a constant value. So as an example, interval coordinates in the bottom left figure can only have a constant value, but not arbitrarily truly continuous functions over those regions. So each coordinate spans on the continuous domain, but the value is actually constant. We can still demonstrate, we can express a lot of fun and various applications, even with this piecewise constant restrictions in the evaluation. And now here's the challenging part. Because the data is spread out very continuously within the interval coordinates, if you naively iterate over all the index I and perform dot product, what we will end up is infinity, as there are infinitely many non-zero points between 2.2 and 3 because non-zero points. There are a lot of non-zero points. So As you could see, the one challenge is considering a reduction on a continuous domain. So we need to be clear what is the semantic of repeating this s plus equal yi addition infinitely many times. So first of all, we introduced two types of reductions on plus equal operator, a summation mode and integral mode. And here I prepared two different continuous vectors, one with only pinpoint coordinates and another with interval coordinates. And summation mode shares a very similar semantic of our traditional tensor programming models. It just aggregates value from each pinpoint, so the result will be 5 plus 6 plus 7. On the other hand, integral mode operation operates on an aggregation with an integral. So from syntactical perspective, we distinguish these two modes in the presence of di in the expression. And in integral mode, this variable s will be 1.8 because the length of the interval is 0.6. And if we do integral reductions on the pinpoints, it'll be 0 because pinpoints inherently are interval with a length of 0. And for interval coordinates, the variable s will end up being infinity because there are infinitely many points in the intervals. And to demonstrate how easy and straightforward, let's consider another example, a radius search query in Google Maps. So imagine you want to count the number of predefined points within a circle of radius r. In the continuous tensor approach, here's how you can write the radius search query. So on the right, I prepare 2D continuous matrix A with a value of 1 at 6 different blue pinpoint coordinates, and rest of them are 0. And you want to write a continuous for loops that outputs the count to be 3 because basically which is the number of blue points within the circle. And here's the code you want. Note that all the for loops in line 2 and 3 are continuous. So in line 2 to the 4, you'll continuously iterate through the red circle with an extra distance checking on the line 4 to keep in the circle. After that, in line 5, you will access tensor A with 2.2 plus dx and 3.9 plus dy, where 2.2 and 3.9 is basically the origin of the circle. So this code will add up all the points within this red circles, and which will end up being the count to be 3. So we built a compiler for this continuous loop using Finch. I won't go detail of compiler implementation in this talk, but as Willow suggested, Finch was originally designed for integer domain, but we extended for the continuous domain by adding some more cool rewriting rules. And our compiler needs basically two things: a code with continuous loops and the descriptions of how the continuous tensor are actually stored in the memory. And the compiler then gives you the code that can actually be run on the hardware. So we demonstrated the effectiveness of these abstractions across 4 different very non-traditional areas that people would have not thought about in tensor programming models. In the red box, saving in the lines of code shows the simplicity in expressing these non-traditional applications through our approach. And on the green box, our generative code also showed the very decent performance compared to the manually written library codes. So among this example, I'll show how trilinear interpolations along the ray sampling would work with this abstraction. To start, imagine a sparse grid that shows a gold key with a rainbow in it. And note that I've illustrated this figure in 2D continuous space for clarity, but the actual implementation occurs in the 3D space. So in the initial phase, we shoot the ray and uniformly sample the points along the ray. So this step is written in lines 1 to 4 in the code below. The for loop in the line 1 is basically represents a discrete iteration over the time, identical what you find in the traditional loop programming model. So nothing special until now. And every sample point x for x, y, z, what we're going to do is we apply trilinear interpolation on the nearby grids. And this process can be expressed through an integral reductions on the continuous loops in line 5 to 9 in a 3D space. And you can see this program is very clearly expressed in just 9 lines of code, whereas the reference PyTorch implementation takes like 80 lines of code. And also, on the single-threaded CPU, our generated code performs better than the PyTorch implementation. And now I'd like to talk about what we can do with these things, even with the restrictions of piecewise constant assumption. And there are a lot of applications that treats geometries. So not only spatial join the spatial databases, there are rasterization and ray tracing, et cetera, but also, there are also a lot of kernels out there in 3D deep learnings as well. And programmers need to think about how to efficiently store these geometries and efficiently store geometries and efficiently process these geometries in various domains. And people in this workshop may know that there are tons of formats to store sparse matrix and sparse tensor that are published for decades. Similarly, there are also a lot of spatial data structures out there through a long history to store this geometry, such as KD trees or bounding volume hierarchy. We believe that this continuous n-dimensional tensor may describe many of them, as they can be viewed as nested bounding boxes. Also, similar to the motivation that Fred had in the Taco compiler, there can be a lot of combinations of choosing appropriate spatial data structures and the algorithms, so which is nearly impossible to handwrite all the cases. So the question is, can we bring these spatial data structures and algorithms into a very single, unified tensor domain if we have this kind of extension to the continuous domain? And lastly, many recent deep learning compilers are targeting MapMul accelerators like tensor cores, NVIDIA's tensor core, by doing a pattern matching on a for loop level. And you may have heard of it. There's another cool accelerator called RT core in NVIDIA GPU to optimize programs using bounding volume hierarchy. So similar to the tensor core, it might also be very interesting opportunity if we can describe the behavior of RT core with continuous for loops and offload the computations to the RT core by doing a pattern matching. I think this is all.
Do we have any questions? Awesome. Okay.
Great talk, Jaeyeon. I had a question on your performance numbers. It looked like there were speedups on all of the code except for one of the convolutions. Could you explain?
Oh, this?
Because of the 5x slowdown.
So the point cloud convolution involves not only geometry processing, but also very heavily tensor computation, the traditional tensor computation. So the Finch cannot generate very high performance dense computation. So that's the reason we weren't that perform.
Really cool talk. Love the idea. I think I have a good understanding of how the pointwise code generation might go through, but I'm having a harder time with the interval, like the integral semantics version of this.
Mm-hmm.
I'm wondering if you can clarify that. My gut is telling me that you need to generate some sort of quadrature code, but I don't know how that goes through in Finch.
I don't know if you are familiar with the two-finger merge intersection.
I'm afraid not, no.
So it's, I'll first do an example on the pinpoint coordinates. So basically, when you try to do an intersection between these two pinpoint coordinates, you have two fingers for each vector. Mm-hmm. And if you know if one finger is ahead of the left finger, if the left finger is, anyway, right. Yeah. It's basically sorted merge in the databases.
Yeah.
And we can apply a very similar techniques to the intervals.
Okay.
So, and Finch can automatically generate such codes.
Interesting. Okay, I have to look more into that. Super cool. And then a follow-up on that is, have you thought about different indexing strategies where there's an I-1 in the setup? At least superficially, that would look like traditional explicit ODE solvers. I'm wondering if you've thought about that at all. I think the semantics might be different underlying this, but at least superficially.
It works, and as you said, that's traditional ODE setup, and it works in our compiler as well. Mm-hmm. But there is some restriction that sometimes basically what you're saying is, can we do affine index expression? But imagine if you do our convolutions on the continuous space, it'll end up in a like piecewise linear, the output. In such case, we can't generate such code because we rely on the piecewise constants. But if we do a convolution code with affine index expressions on the pinpoint coordinates, then it's fine because that will not produce the piecewise linear one.
Yeah, thank you.
Yeah.
Thanks for the great talk. So I have two questions. The first question is that isn't pinpoint computations actually ended up being something similar to what you would do with sparse tensors? Yeah. The second question, especially on the interval part, can you compare it with the work that the spatial databases have been doing? Can you position it somehow?
I think that's a good question.
So perhaps let me give you an answer. Correct me if I'm wrong. Yeah. Can you go back to the Cartesian product slide that it was using the? Yeah. So am I right that you're basically defining a way to generate efficient implementations for each of the physical operators in a spatial database? Am I right?
Yeah.
Yeah, so there is a line of work also in databases which is actually related to code generation, combining code generation with databases, which basically uses multi-stage programming to basically generate efficient implementation of I don't know how many of the spatial join operators, but spatial operators, but it's trying to do that. So I think it would be nice to also kind of position.
But, as far as I know, all of those spatial data databases actually use those spatial data structures and can actually code generate for some special cases. But they use but they can't create a customized kernel that can mimic the KD tree behavior. They just have a single big library implementation for the whole KD tree, and they just call the interface through the already built KD trees. But I think what we are suggesting here is, can we even explain all the behaviors of traversal through the KD trees in a tensor-like style?
I see. Yeah. So I can point you to some relevant work on that line.
Thank you.
Thank you.
So let me see. I think probably we should go ahead and get Paul started to get set up. But Jaeyeon has demonstrated the admirable quality of if you have a short talk, you get to field lots of questions. So let me go ahead and give the mic to Amanda while we're waiting.
Can you talk a little bit more about for the continuous domain why you're limited to piecewise constant functions? Like, would it no longer work if you were using like a pure differentiable function to represent like some continuous value in your interval?
I don't realize you can.
So you're basically meaning, can we do an extension to more piecewise arbitrary functions, right? So that involves a lot of works. Like now it involves like a lot of symbolic computations in it, and we have to build a whole Wolfram alpha. So we're trying to avoid going that direction. But I think that's a really cool directions as well.
I see. Thank you.
Awesome. Thanks. Let's give another round of applause here real quick.
Last one.